This is Phil Coatman with a tutorial on safety plans. A safety plan gives the big picture for your project's safety. Signs that you have a problem with your safety plan include the following. Your safety plan is just a big pile of unrelated documents rather than a structured argument and evidence that demonstrates that your system is safe. Your safety plan does not address software integrity, meaning that it generally assumes the software is perfect and deals primarily with hardware faults. Your safety plan does not link to a relevant safety standard, but rather makes up its own approach to safety. Finally, you have a problem if your safety plan does not at least link to a security plan, because an insecure system is usually an unsafe system. While the details differ depending on your application domain, a safety plan generally starts with a safety standard that is compatible with your application. Within the framework of that safety standard, you complete multiple cycles of the following sets of elements. Hazards are identified and assigned risk levels. Safety goals are created and linked to safety strategies and more detailed safety requirements. And mitigation approaches for hazards are proposed, and analysis determines whether those mitigation strategies meet the stated safety goals. In the typical case, this analysis leads to identification of additional hazards or adjustment of risk levels or the need for additional safety goals. Thus, you end up with a multi-iteration cycle until the hazards, goals, and analysis all converge. During this process, a safety case is created to document the framework for the other parts of the safety plan and results in the end in a methodical argument about system safety. That includes why the system is safe, what about the system is safe, and why an external reviewer should believe that the safety case is both complete and correct. Let's discuss each of the main elements of a safety plan in turn. We'll start with safety standards. Safety standards typically deal with functional safety. Historically, the idea was that there would be a separate safety mechanism that, for example, performed a system shutdown in the event of an unsafe situation. That shutdown system would be the safety function. So the starting point for functional safety is that there are separate safety functions that can be activated to bring the system to a safe state. The prototypical current safety standard is IEC 61508. This standard was specifically designed and intended to be a basis for other domain-specific safety standards. It is also the primary functional safety standard used in the chemical process industry. Other domains have specific standards tailored to their needs, such as ISO 26262 for automotive applications, EN 50-126-8-9 for rail applications, MIL Standard 882 for combat systems, IEC 6730 for consumer products, DO 178 for aircraft, and so on. Each of these standards is a bit different in how it approaches safety, but at a high level, all of them have some key characteristics. This figure shows the steps required by IEC 61508. Safety analysis starts with determining the hazards and risks for the system. Usually, a safety integrity level, or SIL, SIL, is assigned based on the severity of the risk. Higher severity mishaps are assigned a higher SIL. For example, in 61508, a mishap that might result in multiple fatalities or the destruction of a chemical processing plant would be rated SIL 4, whereas a mishap that is quite minor might only be SIL 1. The SIL, in turn, determines the level of engineering rigor required for analyzing and designing the system. A SIL 4 risk requires a tremendous amount of engineering effort and redundant hardware to mitigate the potential for those very severe mishaps. On the other hand, a SIL 1 level of risk requires more or less good engineering care, with some specific techniques being required to ensure that level of care is actually present. SILs 2 and 3 require in-between levels of care, with a higher SIL number requiring more engineering care, more engineering rigor, and the application of more specified techniques. Any good system safety standard takes a life cycle view of safety. That means that it not only covers system design, but also system validation, maintenance, and feedback from observed in-service incidents to affect continuous improvement of safety. It also includes any safety issues relevant to decommissioning and disposal. Once system hazards have been identified, a safety goal is created to identify what safe means with respect to that hazard. For example, in a vehicle speed control application, one of the hazards identified might be unintended vehicle acceleration. The goal to mitigate that hazard might be to ensure that the engine power is proportional to the accelerator pedal position, with a released pedal producing minimal power and a fully depressed pedal producing maximum power. Related to the safety goal is a safety strategy, which is how you plan to achieve that safety goal. For this example, you might decide to have a two-prong approach. First, you would want to make sure that the calculation of pedal position to power output is performed correctly. But because this is a high-sill situation that could result in death, you would probably also want a failsafe that would guarantee engine shutdown if unintended acceleration were caused by either a hardware or software fault in the primary engine power computation. Once safety goals have been created, safety requirements are used to fill in the details. Generally, the safety goals relate to the system as a whole, and safety requirements are more broken down so that they can be allocated to particular subsystems or components. Safety requirements can include both functionality and specific failsafe mitigation requirements. Continuing the vehicle speed example, a normal functionality requirement would be to ensure that the engine torque is properly computed based on the position of the accelerator pedal. But a second safety requirement could be that any pedal-to-torque computation mismatch that might be caused by a system failure would result in an engine shutdown via some independent functional safety shutdown mechanism. A commonly used reliability analysis technique is FMEA, Failure Mode Effects Analysis. Sometimes there's a C in there which stands for criticality, which would be a FMEA, but they're basically the same idea. The idea is you start with a component failure, you analyze the results of that component failure, and you identify the hazards that can result from that component failure, and optionally you add in a criticality, meaning how bad is the problem. FMEAs work with a table that lists the various aspects of the analysis. For example, we have a resistor R2, and a potential failure mode is open, fails open. In other words, there's no electrical current. If you look at how the system is designed, you might decide that's going to trigger a system shutdown. And you might decide a recommended action is to use a better resistor that is less likely to fail because this is low criticality, non-catastrophic failure. And if you're tracking an FMEA, you might keep a status that says, all right, that mitigation has been done. Most components have more than a single failure mode. So that same resistor might fail short, meaning it fails with the current going through with no resistance. In the particular system example here, that might result in an overcurrent or a potential fire. And that might be unacceptable because it's high criticality, so you might need a circuit redesign. And apparently in this particular project, that hasn't been done yet. Every component in the system needs to have one or more rows in this table, so there's a lot of rows in this table. Capacitor C7 might have a failure mode of it explodes, and this really happens to some types of capacitors. The failure effect might be a potential fire, and you might need to pick a different capacitor technology to eliminate the possibility of that failure. FMEAs have significant limitations. In addition to being a very, very big table, they're pretty hardware-centric. They work great for resistors and capacitors and components where it's pretty simple to enumerate some specific failure modes, and often you have the probability as well, so you know how often it's likely to happen. But complex components are not that well behaved. For example, the failure mode for software in the worst case is it fails however it wants to fail. There's no way you can credibly say, well, software will either crash or compute perfectly. Software has bugs, weird things happen. That's just not a credible failure mode. Integrated circuit chips, such as CPUs, are so complex that there's really no credible way to know what all the failure modes are. Even if you look at them on a component-by-component basis in the schematic, you're not accounting for the fact that the wires between the components cross-couple with each other in completely unpredictable ways unless you do a layout analysis. So these types of things, FMEAs are just not that good at. They're also poor at representing correlated and accumulated faults. For example, if a capacitor explodes and it damages several nearby components, an FMEA is not going to expose that because the FMEA assumes one component at a time fails and figures out the results. So that means that FMEAs are pretty good for hardware reliability, but they're not particularly useful for any of the more complex safety critical issues. A common technique for identifying hazards for safety critical systems is known as HAZOP, Hazard and Operability Analysis. The idea of HAZOP is that you can create hazards using a structured brainstorming technique. The brainstorming method works by first looking at each requirement in the system and then modifying it with a guide word, and then asking, does the result suggest a hazard? For example, you might have a list of guide words such as not, or more, or less, or as well as, and those correspond to meanings in, for example, a process flow environment that you quantitatively increase or decrease. And the idea is to take the requirement and modify it with a guide word and come up with an opposite requirement to suggest a particular hazard. It's an effective starting point. It's not guaranteed to find all hazards, but nonetheless, it's a great place to start. Let's do a couple examples. For example, you have a pressure system and there's a requirement that says when the pressure exceeds 6,000 psig, relief valve shall actuate. In other words, you have a classic relief valve that's supposed to open and relieve the pressure if the pressure gets too high. Well, HAZOP says insert the word not and see what you get. When pressure exceeds 6,000 psig, relief valve shall not actuate. Well, if the relief valve stays closed and you have an overpressure situation, that sure sounds like a hazard to me. And so you will take that one requirement and insert every single guide word in it. More, less, part of, reverse, early, late. For example, if the relief valve actuates late, that's certainly an issue, although potentially not as bad an issue as it never actuating. After you go through the guide words, you'll find out that some of them make sense, and some of them just kind of don't make sense or aren't that interesting. You record the ones that sound like genuine hazards, and that's how you do your brainstorming. As another example, you might have the system shall come to a complete stop within 5 seconds when emergency stop is activated. You add the guide word after and replace within to after, and that's one where it's taking too long to stop the system. Sounds like a problem. When you're done with a HAZOP, what you have is a list of hazards that are the opposite of or modifications of or somehow related to violating the requirements that make the system safe. Once you have that list of hazards, then you have to decide what to do about it. The safety cycle typically begins with identifying hazards, which are potential sources of injury or damage. In other words, a hazard is a potential cause of a mishap or loss event involving personal injury, death, environmental damage, or some other form of unacceptable loss. A hazard log is used to record hazards identified for a particular system. The hazard log starts with a list of hazards from any similar legacy system to capture lessons learned from previous projects. Additional hazards are added, first by analysis, and later by recording field experience after the product is deployed. Analysis is often performed by a method called HAZOP. A HAZOP works by applying modifiers to system requirements. For example, if there is a requirement for speed, a HAZOP would modify the wording of that requirement with keywords such as too fast or too slow to help in brainstorming what might happen if the system was faster than the required speed or slower than the required speed. Once hazards have been identified, each is assigned a risk. Intuitively, a risk can be thought of as the product of the probability of a mishap times the consequence of that mishap, often equated to dollars. Those per mishap risks are added up to get the total expected cost of system failures. In practice, this mathematical approach has problems because it is difficult to create precise numbers for both the probability and the consequence. It also has trouble with very low probability events that have extremely high negative consequences. Thus, it is common to see a risk table approach as shown by this figure. With the risk table, consequences are placed into perhaps a handful of bins, with each bin covering more or less an order of magnitude in severity. Any consequence on the border of a bin is rounded up to the next most severe bin. Thus, consequences form the rows of the table. The columns of the table have to do with probability. Again, probability is put into a few bins, usually with an order of magnitude or two difference between adjacent bins. The risk for each mishap is rated by looking at the intersection of its row and column in this table. In this example, the upper left square of very high consequence and very high probability might refer to a mishap that could result in multiple fatalities and would, if not mitigated, happen on a daily basis for a deployed fleet of systems. Such an obviously problematic situation would be rated as a very high risk according to this table. Each safety standard, and potentially each safety project, might have slightly different arrangements of risk values for the squares of the table, but in general, the upper left of the table has the very high risks, which correspond to very high SIL requirements, while the lower right has low risks that correspond to low SILs. In this example table, a very high risk probably corresponds to SIL 4 in IEC 61508. Once a risk has been identified, that SIL stays the same even though the risk has been mitigated to an acceptably low probability. Once safety requirements have been identified, analysis is used to determine if the system design meets those requirements. A failure mode effects analysis, or FMEA, is often used to deal with hardware faults in system reliability. An FMEA starts by hypothesizing that a hardware fault occurs. It then works forward from the known particular failure modes of that particular component to see what mishap might result. FMEAs are helpful, but quite limited for safety because they do not deal with multiple fault scenarios, they do not represent correlated hardware faults, and because software can fail pretty much any way it wants, so an FMEA's assumption that software fails in known ways often does not work for safety. For safety, a fault tree analysis, or FTA, is also required. Fault trees work by starting with a mishap or hazard and working backwards towards the possible causes. Here's an example showing that a fault tree is kind of drawn upside down, with the root of the tree at the top and the leaves at the bottom. In this example, a hazard or mishap is at the top of the tree, at the root, and working downward toward the leaves. There are nested levels of AND gates and OR gates. An OR gate means that any one of the inputs below will, if true, cause the hazard. An AND gate means that all of the inputs below that gate must happen concurrently for the hazard to be caused. With this formulation, it becomes clear that AND gates are good because a single fault cannot produce the hazard if it goes through an AND gate. On the other hand, OR gates are bad because they document multiple potential ways for a hazard or a contribution to a hazard to occur. This insight from fault trees leads to the conclusion that for life-critical systems, you must have no single points of failure. That, in turn, means that a fault tree must have no paths from a leaf to the root that passes only through OR gates. If all paths go through at least one multi-input AND gate, then there's no single component that can cause system failure. More generally, considering a single point of failure is asking the question, if a single component breaks, is the system unsafe? And that question has to be asked of every component in the system. Asking this question can be subtle and tricky in practice because when a component breaks, it does not necessarily just go silent. Rather, and especially with computational elements, a component failure can happen in the worst possible way for the system. In general, there is no way to guarantee that software will fail in a well-behaved way. Thus, software failures have to be presumed to do their worst to try to make the system unsafe. For our vehicle speed control example, any single computer in the system must be presumed to fail, for example, commanding full engine power, which is unsafe. That's why a safe engine controller has two computers working in tandem, so that if one of them fails, the other can at least perform a system shutdown. In practical systems, avoiding single-point failures is a start, but not quite enough. There may also be likely sets of correlated faults that affect multiple components. Additionally, independent failure arguments generally don't work for software, so software on two different components might fail in the same way. That's handled by developing software to the highest SIL needed for the system and ensuring that, for practical purposes, the software is perfect in that it will not exhibit unsafe behavior. The cycle of identifying hazards, creating safety goals, and mitigating risk results in a safety case being generated. The safety case demonstrates that a system must be safe because of a combination of a structured argument and evidence to support that argument. The argument can include use of design elements, use of rigorous engineering processes, and use of certified components in a system, among other things. However, each argument must be supported by objective evidence that demonstrates that, for example, design elements were implemented correctly, or the rigorous engineering process specified was actually followed, or third-party component quality is documented by a suitable safety certification. Thus, the safety case will incorporate written descriptions and evidence for at least the following: a methodical identification of hazards, an evaluation of each hazard to determine its risk, appropriate mitigation and rigor used as determined by the risk's SIL, and analysis, testing, or other means to ensure that mitigation actually was completed successfully. Additionally, it must be shown that the safety requirements appropriately cover all hazards, including hazards arising from design faults, operational faults, and even credible malicious faults depending on the system context. Because malicious faults can and do occur in the real world, this means that the safety case has to link with a suitable security case at the very least. While there are a number of approaches to creating a structured safety case and tools to support them, an emerging tool worth considering is Goal Structuring Notation, or GSN. At a high level, the general idea of GSN is to take a fault tree and annotate that fault tree with the argument and evidence required to demonstrate that the hazard at the root of the fault tree has been adequately mitigated. The best practice for creating a safety plan is to create a written plan specifying the steps, arguments, and evidence that will be used to demonstrate system safety. In other words, the safety plan defines the process by which you will produce your safety case. The safety plan should, at a minimum, address hazards, risks, safety goals, safety requirements, analysis techniques, how you plan to evaluate mitigation effectiveness, which safety standard you plan to follow, the format of the safety case, and how you plan to independently audit that safety case. It is essential that any safety case be independently checked to ensure that no steps were skipped and that there really is suitable written evidence that required engineering rigor was actually applied. Beyond ensuring that the safety plan was actually followed as it was supposed to be, there are a few pitfalls that commonly arise when executing a safety program. First, it is essential to evaluate the quality of the software to make sure it is sufficient for your safety level. For life-critical systems, the only practical way to assure sufficient software quality is usually to apply rigorous engineering approaches as specified by the relevant SIL in the safety standard you're using. Testing is insufficient to assure life-critical software quality. While engineers are comfortable using FMEAs for hardware analysis, FMEAs aren't enough for safety because they can miss correlated faults and multi-point faults. This is especially true for faults caused by software defects. Thus, it is essential to use fault tree analysis to augment any FMEA when creating a safety case. Finally, it is also essential to include security attacks in the safety case. If the system is not secure, it is unlikely to be safe. At a minimum, each hazard in the system needs to consider the possibility that the hazard was activated by a security attack and use appropriate mitigation techniques to prevent that from happening. In practice, this means that almost certainly you'll want your safety case to be tied in to your security case.